Right, so last time we met, we were talking about some vocabulary of making solutions, right? We talked about taking a pile of a material, putting it into something like water, and the result we called a solution. Now, what did we call the material that we're going to add to our water for our solution? Do you remember? Solute. Very good. And what was this one? What was the water called? Solvent. That's right. We have the solute and the solvent. Excellent. And the mixture, what do we call the mixture? It's a solution, right? A solution is a mixture between the solute and the solvent. Very good. And we also talked about what happens when you take an ionic compound like sodium chloride and put it into water, right? What happens when I put something like sodium chloride into water? What happens to it?
It turns sodium chloride acid.
Ions. It turns to sodium ions acid and chloride ions, right? And we write AQ to show that those ions are dissolved in water. Okay. Okay, so we have to begin to recognize that if I have a salt like sodium chloride or any salt that's soluble, and we also introduced last time a table, right, of solubility in which we can look and see what compounds are, what ionic compounds are soluble in water. That means they dissolve in water, right? And so when we find an ionic compound that dissolves in water, we write it like this, NaCl aqueous. That means sodium chloride dissolved in water. But we have to remember that really what's happening is that these ions are separate like that, being entertained by water molecules. And this can happen with not just ionic compounds. It can also happen with stuff like sugar, or glucose. We can use glucose for an example. C6H12O6, that's the chemical formula for glucose. You put it into water and it will dissolve. So here, this is solid. And then I get C6H12O6 and I write aqueous there. But it doesn't dissociate into ions the way an ionic compound does. All right. So both of these we say dissolve. Right? Both of them dissolve. Two in there. But only this one here. Do you remember the word? What is this one doing that the other one's not? Dissociate. Dissociate. Very good. And what that means is the ions actually separate from each other. And that's also why water becomes conductive if it has ions dissolved in it. So let's look right here. We see that sugar can be dissolved in water just like salt does in terms of it can also be dissolved. But sugar does not dissociate into ions because sugar is not an ionic compound. Okay. And this is what I just... What's that?
I have a question.
Yeah, what's the question?
What's the thing for sugar?
The thing for sugar?
I have a question.
Well, sugar is called sucrose. So let me bring up here
the
web
for
page,
sugar.
and we're going to look up chemical formula for sucrose. It's very similar to that of glucose, but it's just twice as much of the carbon and almost twice as much of the hydrogen and oxygen. Okay? And the reason why it's almost twice as much, if you look at a chemical of sucrose, just this half right here, this is sucrose, but if I just take one half there, that is the chemical formula for glucose. So glucose twice, and this is another molecule that's very similar to glucose called fructose. Two glucose molecules essentially bound together, or it's really one glucose and one fructose. But the idea is that both of glucose and fructose have the same chemical formulas. But here, when they bind together, they lose a water molecule, an oxygen and two hydrogens, and that's why we get a change in the formula. So the chemical formula for sugar is essentially the same as the chemical formula for two glucose molecules, which is C6H12O6, that have come together and lost a molecule of water. Okay, that's a good question. Now, here's a question for you. If I put sugar into water, well, let me start that question. If I take salt and put it into water, does it make the water conductive? No. It does. It does. Do you remember how we drew a picture a while back of a light bulb and having two wires, but the wires don't touch, and so it won't light up unless there is something to make those two wires conduct electricity back and forth. And you can either connect them with a wire. So let me draw here. Now, we don't want to make anybody think that conductivity means that we're creating energy, because we're not creating energy. But I have a battery here, and this end of the battery is going to go and touch the side of the light bulb. Okay? And this end right here is going to touch the other end, the bottom of the light bulb. However, we're not going to let these wires touch together, right? So this is my conductivity experiment. If I lay something conductive across there, then the light will light up, right? Because then the electricity can flow from one side of the battery to the other. If I put this in a cup of water, here it is, water, the light won't light up because water is not conductive. But when I put some salt in there, some chloride, what happens is the sodium ions and the chloride ions can help conduct the electrons back and forth, so the result is a conductive solution, and the light will light up when I put my sodium chloride in there. Okay? So the ions in sodium chloride result in a conductive solution. So here's the question. C12H 22O11. That's the chemical formula for sugar. If I put sugar solid into water, what will the result be? I mean, will it dissolve? Sugar, if I put sugar into water, do you know if it dissolves? It dissolves, but it doesn't dissociate. Because it's not ions, is it? This isn't an ionic compound. How could I tell that was an ionic compound? There's no metals, right? There's no metals. It's all non-metals. Right? Good. So when I put it in water, it will dissolve, but it will not dissociate. It will not dissociate. Therefore, if I put sugar into water, and that's what this is over here, this is a solution of sugar in water, the light won't light up. If I put it in a solution of copper sulfate, that's another salt, that does dissolve in water, the light will light up. It doesn't need to be just sodium chloride. An ionic compound that will dissociate will make the light light up. Now there's a special word for a compound that will add conductivity to water when you put it in there. And that word is electrolyte. Electrolyte. Okay? So, electrolyte for a long time. People didn't know what electrolytes were, and there was a company that sold water with flavor and electrolytes, and everybody said, sounds interesting. Electrolytes, what are they? I don't know. Let's eat. It must be better. And so they sold a lot of money, or sold a lot of drink, telling everybody that they needed to have their electrolytes. But electrolytes are just salt, right? So it's important, if you're working hard, to make sure you get plenty of salt in your diet, because when you sweat, you lose salt, and your body needs to have an amount of salt so that all of your cells can function well. And so it's important when you're sweating a lot to make sure you drink some electrolytes. But you don't need to necessarily buy a sugary drink to get that to occur. There's other ways that you can get electrolytes just by eating food. Okay, so now we're going to introduce terms called these three terms, which are strong electrolyte, weak electrolyte, and non-electrolyte. Okay? And what this means basically is, what it's referring to is the ability for the compound to create or result in ions when it's placed in solution. So sodium chloride, we say, is a strong electrolyte, because when you put it into water, it dissociates, into ions. All right, that's what the definition of a strong electrolyte. You put it into water and it completely dissociates into ions. A non-electrolyte would be an example of C6 or H. Glucose would be an example of a non-electrolyte. C6H12O6. You put that into water, and is that going to form ions when I put it into water? C6H12O6? No, because it's not what? It's not an ionic compound. That's right. So it'll be aqueous, and I could write aqueous by all of these ions up here as well. Okay? But this compound can dissolve in water, but it's a non-electrolyte, because when it's placed into water, it doesn't result in ions being created. And now there are some compounds out there that you put them in water and they will dissociate, but just a little bit, just a small amount. And so those are called weak electrolytes. So basically, if you put them into this sort of an apparatus, there would be a little bit of light show up, because a little bit of electricity could transfer through the solution. But not very much, because a weak electrolyte only partially dissociates. Okay. So, when we write sodium sulfate, for example, this is sodium sulfate, as a solid here, and we show that it dissociates, we need to be able to recognize the number of ions. For example, Na2SO4 is going to result in 2 sodium ions and 1 sulfate ion. And it's important that we put the correct charge on the sulfate ion and the sodium ion. And as we said, we want to make sure we have the correct coefficient as showed as in the initial compound, right? Sometimes we won't write aqueous, which isn't terrible. It's okay, because we're just recognizing that sodium ions are, there's no way that they can just kind of exist without the water to dissolve them. So if I have a dissociation equation like this, then basically we know that it's occurred in water. Okay, so let's write the resulting dissociated products when we take these different salts and put them into water. Do you know the name of this top salt here? What's the name of that salt right there? Sodium phosphate. Very good. Let's write the dissociative products of sodium phosphate when it dissolves. Okay? what does it have in it? Or what are the resulting ions when sodium phosphate goes into water?
Sodium phosphate.
Not positive 3, positive 1. How do we know that? That's right. Its location on the periodic table allows us to remember the +1 charge. So sodium with +1 charge. And what's the other ion that we get?
Positive 3.
Phosphate. What's the charge on the phosphate ion?
Positive. Because it's one away from
-3. Now, how did you get that? How did you get the -3? What did you have to do to find the -3? All right, that's good. It's good to look on the back of the periodic table.
phosphate.
There's another way I could tell that it was going to be a -3, though. You know how? Even before I looked on the back of the periodic table. You know how I knew?
Negative.
Because there were 3 sodiums for every PO4. You see that? And so because I knew that sodium had a +1, if there's 3 of them, that means the PO4 must be a -3. Can you see that?
I looked on the back of the periodic.
Excellent. So what we have here is the sodium phosphate dissociating into 2 ions, or 2 different kinds of ions. But now I need to make sure I have the right number of ions. Do I need a coefficient in front of either one of these ions? How many sodium ions do I have over here before it dissociated? 3. So I need to make sure I have 3 over here. So I'm going to put a 3 in front of there, because I have 3 sodium ions. Once this dissociates, I have 3 sodium ions and 1 phosphate ion. And then it's nice to write the aqueous like that. Okay? Very good. So let's do the next one. What's the name of that next compound there?
No.
Al is element 13.
3.
Uh-huh. Aluminum sulfate. Aluminum sulfate. Very good. So let's write the ions that will result when aluminum sulfate is placed into water. What are the ions that will result?
Aluminum. Sulfate.
Positive what? 4? Where's aluminum at on the periodic table? What does it have to do in terms of its electrons? It's number 13, right? It adds 5 electrons, or does it lose 3? That's right. So it's a +3. It's to the left of that staircase. It's a metal, so it's going to want to lose electrons. All right. And what's the other ion? Not the aluminum, but what's the SO4? Uh-huh. What is the charge on the sulfate ion?
5. Yeah, so I have to move 5.
1.
Oh,
Let's see if I can find my polyatomic ion chart. Can you find it? -2. -2. Okay, very good. And there's a couple ways that I could have seen that as well. Because remember, our crisscross rule can work the other way when we're trying to find out what the ions are, right?
1.
Okay, so now what coefficients can go in front of this aluminum ion and the sulfate ion? How many do we need over here? And how many sulfates?
-2.
2 aluminum. Okay. Sulfate. Very good. 3 in front of sulfate. And then we'll write in here aqueous to show that these are dissolved in water. Excellent job. Okay, so the next one, CaCl2, what's the name of that compound? Calcium chloride. Very good. Excellent job. All right. What are our ions that are going to result when we put calcium chloride into water?
2 in front of aluminum. Yeah. And 3 in front of phosphate.
Calcium plus 2. Chloride, good. Minus 1. Very good. Do we need any coefficients in front of either of these?
Calcium chloride. Chloride.
Like, isn't there 2 chlorides? Very good. That's right. And then we write our aqueous like that. Okay, excellent. All right, let's see for our last one. What's the name of that compound there?
Calcium. Permanganate.
Very good. Very good. Calcium permanganate. All right, so calcium permanganate, when placed into water, what are the resulting ions?
Calcium.
What's the charge?
+2.
Positive 2, that's right. And?
Manganate.
Permanganate, that's right.
Permanganate.
And what's the charge on the permanganate ion?
1.
Minus 1. Remember, you can't just say 1, 2, or whatever, and you can't just say positive or negative. You always have to say positive 1 or negative 2 or whatever, right? Now, how many calcium ions am I supposed to have here on the left?
That's
Yep.
it.
How about permanganate? 2.
2.
And then again, our aqueous. Okay, very good. Excellent job. So, which of the following would not be expected to produce a chloride ion when it dissolves in solution? Okay. What do you think?
Is it Wait. Isn't chlorine?
Which of the following would not be expected to produce chloride ion when dissolved? If I put sodium chloride into water, am I going to get a chloride ion floating around?
Yes.
That's right, I am, because it's an ionic compound, and it will ionize or dissociate when placed in water, so I'll get the chloride ion. What about lithium chloride? What?
Oh, it's
Why?
It's Aron.
It's not an ionic compound.
Very
Because
good.
it's not
It's
an
a molecular
ionic
compound.
compound.
Therefore, you put it into water, and the chloride ion is not going to be there. Fabulous job. Way to go. How many ions form dissociation, or this should say upon the dissociation of sodium phosphate. How many ions do I actually get when sodium phosphate dissociates? And remember, notice that it's not asking how many kinds of ions, because there's two kinds. There's sodium ions and phosphate ions. But how many ions altogether, right?
What's an ion again?
An ion, like here, let's use calcium chloride as an example.
Ion again?
You put calcium chloride in, and I get the calcium ion and 2 chloride ions. So that's a total of 1, 2, 3 ions.
Oh.
3.
Get it.
Oh. So you put that in, and you get 1.
Let's look here. What kind? Oh, I have them right here, right? We did this one already.
Ooh. 4.
4 ions. Very good. 3 sodium ions and 1
Ooh.
phosphate ion.
4.
How about this one? How many ions do I get when we dissociate aluminum sulfate? 5. Very good. Excellent job. Okay, very good. So,
5.
when we write a chemical equation, so here's an example of a chemical reaction. Here I have this compound here. Do you know the name of that compound, AgNO3? Okay, let's see if we can learn it by looking at the periodic table. Ag is element 47.
No.
Silver.
Very good, silver. Ag and NO3. What do you think NO3 is?
Silver.
Oh, let's look at our periodic or our polyatomic ion chart. There it is. I see it. You see it?
Nitrogen.
Nitrate.
Very good. Very good. So the name of that compound is what?
Is
Very
nitrate.
Silver nitrate plus, what's the name of this compound?
Silver nitrate.
K is element 19.
Potassium chloride.
Very good. Silver nitrate plus potassium chloride come together and react to yield.
Potassium chloride.
Silver chloride.
And
Potassium nitrate.
yeah, potassium nitrate. Very good. Excellent job.
Silver chloride.
Yeah, what's that?
Potassium nitrate? No, potassium.
It's like every time it ends with a 3,
Wait, I have a question. It looks like every time it ends with like a 3, like
4. Chromate. 4. And
like phosphate ends in a 4.
hydrogen sulfate.
Chromate
Yeah.
ends in a
All
4.
ends in 8.
And
Oh, that's a very good recognition.
hydrogen
Good job.
sulfate
Yeah.
ends in a 4.
And
All ends in
sometimes
8.
the 3s end in 8s. Well, here's a C2O4. That's oxalate. That's right. If it ends in 2, here's a nitrate, or a chlorite, ends in NO2, nitrite, SO3, sulfite. Very good. Very good observation. Yeah. Okay. So, this equation here, we can read it. We're pretty good at reading equations. It says silver nitrate reacts with potassium chloride to form silver chloride and potassium nitrate. And now we have another way that we can kind of write this. We can write what's called the ionic equation, where we take everything that's aqueous, See, this silver nitrate is aqueous. The potassium chloride is aqueous. And the potassium nitrate is aqueous. The silver chloride is solid. That means it doesn't dissolve in water. We can take that equation here and make everything that dissolves and dissociates, we can separate it as ions. You see that? So silver nitrate aqueous, I rewrite as silver ions and nitrate ions. See how that happened? And then the potassium chloride here, KCl, I rewrite it as K plus ion and Cl minus ion. Can you see that?
Yeah.
Okay. How did I rewrite the AgCl solid? Did I separate it into its ions?
Some of them you did.
The AgCl here? See?
Yeah, that's one.
Now see down here? It's not separated, is it? It's
Some of
still
them you did.
together because it's not soluble. It doesn't dissolve
Yeah,
in
that's
water.
one.
And we could verify that. We could look at our solubility
Yeah.
rules here and remind ourselves that Rule 3 says chlorides are soluble except silver, lead, and mercury. So here with silver chloride is not soluble. But then KNO3 is, that aqueous sign means it is soluble, and so I write that as ions, potassium ion and a nitrate ion. Very good. So what we're writing there is our ionic, we call it. We start with the chemical equation or a molecular equation, sometimes people call it. I don't like that name though because there's nothing molecular about this. And then the chemical equation can be rewritten as in the form of an ionic equation. Okay, very good. That's a good place to stop for now. Thank you very much.